Greetings and welcome to another walkthrough of a Math Olympiad. In this episode, we'll be looking at the junior section round 1 for the Singapore Mathematical Olympiad in the year 2020. Hosted by the Singapore Mathematical Society, the SMO is the oldest and most prestigious math competition in Singapore. The junior section category is for students up to an age limit of 14 years old. It consists of 25 questions in total, with 5 multiple choice questions and 20 open-ended questions, with integer answers ranging from 00000 to 99999. The top scorers for this competition would be invited to round 2. So let's begin with question 1. Let x equals to 2 to the power of 300, y equals to 3 to the power of 200, and z equals to 6 to the power of 100. Can we arrange x, y, and z in descending order? Pause the video here and give this question a good try. So in question 1, we want to compare indices. We can make them either have the same index or the same base before we compare them. So let's look at x. We can change 2 to the power of 300 to 8 to the power of 100. This is using the power law. For y, we can convert it to 9 to the power of 100. And z will be just as it is, 6 to the power of 100. Therefore, we can conclude that 9 to the power of 100, the base 9 is bigger than the base 8, which is bigger than the base 6. So y is greater than x greater than z. Question number 2. An expensive painting was stolen and the police rounded up 5 suspects, A, B, C, D, and E. Statements were then recorded. A said, either B or D stole the painting. B said, I think D or E is the guilty party. C claims that it must be D. D claims that B or E did it. And E said that I am absolutely sure that the thief is A. Only one suspect stole the painting and all 5 were lying. Who stole the painting? Pause the video here and give this question a good try. So to tackle this question, we need to take the logical complements of each statement. So for example, from statement A, either B or D stole the painting, the opposite would be that not B and not D. B and D are both exonerated from this crime. We can then exonerate D and E from B and so on. This leaves that C must be the guilty party. Question number 3. The following diagram shows a system of balancers hanging from the ceiling with 3 types of weights. The balancers tip down to the heavier side. Arrange the 3 weights from the lightest to the heaviest. Pause the video here and give this question a good try. So we just need to break this diagram down. We first look at the top left box here. You can see that the triangle must be lighter than the circle. If we look at the bottom right corner, now we can tell that the triangle is also lighter than the square because anything that's at the bottom is heavier. Now if we look at the entire system, we can see that 1 triangle plus 3 circles is lighter than 1 triangle plus 1 square plus 2 circles. We can cross out the triangles and 2 circles on each side. This tells us that the circle must be lighter than the square. This allows us to arrange it, so a triangle is lighter than circle, lighter than square. Question number 4. The integer 6 has exactly 4 positive factors, 1, 2, 3, and 6. The integer 8 has exactly 4 positive factors, 1, 2, 4, and 8. How many integers from 9 to 50, inclusive, have exactly 4 positive factors? Pause the video here and give this question a good try. So for this question, we first need to make the observation that any number that consists of 2 prime factors only will have 4 divisors. So if the 2 prime factors are P and Q, the 4 divisors will be 1, P, Q, and PQ. Now we just need to list out all such numbers methodically. So we can go with the multiples of 2 with a prime number. So it could be 2 times 5, 2 times 7, all the way to 2 times 23. Then we go on to the multiples of 3. It could be 3 times 5, 3 times 7, up to 3 times 13. We go to the multiples of 5, 5 times 7, and that's all. There will be no other such number between 9 and 50. Next, we need to look at the second case. There are also cubic numbers. Cubic numbers like p cubed will have 4 divisors, 1, p, p squared, and p cubed. And there is one cubic number between 9 and 50, and that is 27, 3 cubed. So in total, we'll have 12 plus 1, which is 13 such numbers. Question number 5. A company sells a bottle of juice at $1 per bottle and offers to give you a free bottle of juice if you recycle 4 empty bottles. Assuming there is no limit to the offer and you can recycle bottles you receive from the offer, what is the largest number of bottles you can eventually consume if you have $43? Pause the video here and give this question a good try. So for question 5, we're just going to simulate what happens. So we start off with $43. We can just buy 43 bottles. From that 43 bottles, we'll recycle 40 of these bottles. That gives us 10 new bottles plus the 3 remaining bottles that we didn't recycle. So now we have 13 bottles in total. The 13 bottles, we'll recycle 12 of the bottles. This gives us 3 new bottles, and we still have to carry over the 1 remaining bottle from the 13 earlier. So now with the 4 bottles that we have, we'll recycle all these 4 bottles, and we'll get 1 new bottle. So we'll just add up all the new bottles. So we have 43 plus 10 plus 3 plus 1. In total, we'll have 57 bottles in all. Question number 6. Let n be a positive integer. Suppose the LCM of 4, 5, and n is 2020. What is the sum of the smallest possible value of n and the largest possible value of n? Pause the video here and give this question a good try. So if we prime factorize 2020, that's going to give us 2 squared times 5 times 101. So 2 squared is already 4, 5 is already there. So the smallest value of n has to be 101, the remaining prime factor that hasn't been accounted for. The largest possible value would be all the prime factors included together, which is just 2020. So if we sum these two numbers together, our answer will be 2121. Question number 7. When the 5-digit integer 2x6yx concatenated together is divided by the 4-digit integer 5y27 concatenated together, the quotient is 4 and the remainder is x106 concatenated together, which is a 4-digit integer. What is the value of the digit x? Pause the video here and give this question a good try. Now, normally when we think about division, we think about something like 7 divided by 3 gives us 2, and 2 times 3 is 6, and there will be a remainder of 1. So we normally do this kind of long division working. The 7 is known as the dividend, the divisor is 3, quotient is 2, and the remainder is 1. But we can rearrange this working. We can always put it as 7 equals to 2 times 3 plus 1. In other words, the dividend is equals to the quotient times the divisor plus the remainder. Now we're going to use this idea. So now we can take the dividend of 2x6yx equals to the quotient of 4 times the divisor of 5y27 plus a remainder of x106. Now we shift the remainder over to the left-hand side, so we'll take the dividend minus the remainder, and we can break this down further. We can simplify it because 2x6yx minus x106 in the units place, x minus 6 is just simply x minus 6. In the tens place, y minus 0 is y. In the hundreds place, 6 minus 1 is 5. In the thousands place, x minus x is 0. In the 10,000s place, it's just 2, so there's nothing changes there. So we can rewrite that on the left-hand side. The left-hand side becomes 2051x minus 6. Now, for the right-hand side of 4 times 5y27, we can split the 5y27s and we can extract the y from the hundreds place. So that will become 5027 plus 100y. Then we'll just multiply that by 4. That gives us 400y plus 20,108. Now from here we can already work out the answer for x, because if you see, if I bring the 6 over to the right hand side, the x has to be 4, because that is just 4 times 7. You just look at the units place. 4 times 7 plus 6 is 34. Therefore x has to be the last digit of 34, which is 4. We can also work out the y. We can work out a y because we have 5y4. Once we replace the x with 4, 5y4 will be equals to 400y plus 114, which is the 108 plus the remainder of 6 from the left hand side. And if you just observe this, you can tell that y must be 1, because if y is 0, it will be too small. If y is 2, it will be too big. You can just guess that y is 1. But let's not just assume that y is 1 and x is 4. We can also verify this entire thing out. We will sub that all back in. Is 24614 divided by 5127 equals to 4 remainder 4106? Yep, it will check out. Question number 8. How many multiples of 11 are there in the sequence 1100, 1101, and so on all the way to 2020? Pause the video here and give this question a good try. So what we need first is the number of multiples from 1 to 2020. So we'll just take 2020 divided by 11 and round it down. So there must be 183 such multiples. Next, we can easily count the number of multiples from 1 to 1099. That will just be 1099 divided by 11 rounded down. So there's 99 such multiples. So the answer we're looking for would be the number of multiples from 1 to 2020 minus away the number of multiples from 1 to 1099. So that's 183 minus 99, which gives us 84. Question number 9. A quadruple A, B, C, D of positive integers is skewed if the median and mode of A, B, C, D are equal, but strictly greater than the mean of A, B, C, D. How many skewed quadruples of positive integers are there that satisfy A less than or equal to B, less than or equal to C, less than or equal to D, and the sum of A to D is equals to 40? Pause the video here and give this question a good try. Since we know that the median and the mode are equal, then B must be equals to C. And since it's greater than the mean, that means B equals to C must be greater than 10, which is the sum of A plus B plus C plus D divided by 4. So now we can just look at possible cases. We'll look at the case where B equals to C equals to 11. Then the sum of A plus D must be 18. Then we can list out all the possible cases. We can just try from AD equals to 7, 11, 6, 12, all the way to 1, 17. You can't get smaller than 1 because A is a positive integer. Next, we can look at B equals to C equals to 12. Well, A plus D must be equals to 16. Then we can look at possible cases. So it's 4, 12, 3, 13, all the way to 1, 15. You can also see that it obviously starts from 4, 12 because D has to be at least C. So we'll start from 12 and go up, and A will slowly go down to 1. In case 3, B equals to C equals to 13, A plus D will have to be 14, and there's only one possibility. Since D has to be 13 or larger, and A has to be 1 or bigger, there's only one possibility of 1, 13. No other things would fit there. We don't even have to look at B equals to C equals to 14 because you will have an immediate contradiction, since A plus D will be 12 and D has to be at least 14. So there'll be no outcomes there. So we just have to count all the cases that we have. There's 7 cases in case 1. There's 4 possibilities in case 2, and there's 1 possibility in case 3. So a total of 12 possible sets of quadruples. Question number 10. Let Tn be the linear sequence given by T1 equals to 10, T2 equals to 13, and so on. and Sn be the quadratic sequence given by S1 equals to 10, S2 equals to 23, and so on, what is the value of S101 minus T101? Pause the video here and give this question a good try. So the linear sequence Tn can be expressed as An plus b, where a is the arithmetic difference and b is the zeroth term, T0. So the term before 10 would be 7. And you can see that the gap between the numbers is plus 3, therefore Tn is 3n plus 7. And you could also work out the general formula for the quadratic sequence in the form of an squared plus bn plus c, but that's not necessary at all. The better way to solve this problem is to observe that actually the quadratic sequence is the sum of the linear sequence above. You can see that S2 is equals to T1 plus T2. S3 is equals to T1 plus T2 plus T3. So knowing that, we can express Sn as the sum of 3r plus 7 from r equals to 1 to n. So if we want S101 minus T101, that will be just S100. Then we can evaluate the sum of 3r plus 7 from r equals to 1 to 100. So using our rules for arithmetic progressions, there will be just 3 times the sum of r from r equals to 1 to 100 plus 100 times of 7, which is just 700. So we'll just put that in the formula, 3 times 100 divided by 2 times 100 plus 1 plus 700. That gives us a total of 15,850, and that's our final answer. Question 11. Let ABC be a triangle where D is the midpoint of BC and E lies on AC such that the ratio of AE to EC is 3:1. Let F be the intersection of AD and BE. If the area of the triangle ABC is 280, what is the area of the triangle BFD? Pause the video here and give this question a good try. So for this question, we first need to construct a diagram. So we're going to draw triangle ABC. Just draw any random triangle, label ABC, and mark D as the midpoint of BC. And we'll have E here as a point on AC, where AE to EC is in the ratio of 3:1, and F as the midpoint, not the midpoint, but the point of intersection between BE and AD. Next, since we know that D is the midpoint, these two yellow triangles that I've drawn at the bottom, they must have the same area because they are triangles of the same height. So their areas, let's just mark it as X respectively for both triangles. Next, since we know that the ratio of the sides AE to EC is 3:1, then these two orangey looking triangles must also have areas in the ratio of 3:1 because they are also both triangles of the common height. So let's just mark their areas as 3y and y respectively. Using that same idea that the ratio of the base is 3:1 for AE to EC, then the big triangles ABE and BEC, they also have to have a ratio of 3:1 for their area. Therefore, the blue triangle ABF has to have 3 times the area of the yellow triangle, which is already we have marked as 2x. So ABF, the blue triangle, has to have an area of 6x. Now, if you examine the bad triangle, triangle BAD, that's half of the entire triangle since BD is half of BC. So 7x, the area of the triangle BAD, has to be half of the total area, and that gives us 7x equals to 140. Now the area of triangle BFD that we're trying to find, that's equals to x, and that's 1/7 of the area 140, and 1/7 of 140 is just 20, and 20 is our final answer. Question 12. In the figure below, each distinct letter represents a unique distinct digit such that the arithmetic shake plus shake equals to rattle holes. If the letter K represents 6, what number does shake represent? Pause the video here and give this question a good try. So let's first work on the low-hanging fruits. We know that the k's are 6. We also know that in the ones column, e plus e gives us a digit of e. And if you just try all the numbers, 1 plus 1, does it end with 1? 2 plus 2, does it end with 2? Nothing works except for 0 plus 0 would also end with 0. So we know that the e's in the ones column must all be zeros. Next, what else can we deduce? Well, if s plus s gives us a and it carries over something to form a r, the r has to be 1, because there's no way you're going to get anything bigger than 100,000 here. The biggest it can be is 99,999 plus 99,999. That will not even reach 200,000. So we know that the r has to be 1. Next, what else can we work out? Well, the 6 plus 6 gives us 12. So L has to be 2, and we're going to carry over a 1 over to the hundreds column. And since we get 1 plus A in the hundreds column, T has to be odd. That means the T in the thousands column is also odd. So H plus H is 2H. That's always even. So that means that another 1 has to be carried over into the thousands column. The next observation that we can make is that H and A is going to differ by 5. And this is because 1 plus A in the hundreds column produces the same last digit T as 1 plus H in the thousands column. So it could be pairs like 1 and 6, 2 and 7, 3 and 8. You can see that 3 plus 3 last digit is 6, 8 plus 8 last digit is also 6. So the pairs have to be numbers that differ by 5. So we can just try out possible pairs, and we know that A has to be the bigger one since A rolls over a ones to the thousands column. So we could try A equals to 6 and H equals to 1, but 6 is already used. We can't do that. We could use A equals to 7 and H equals to 2, but 2 is already used. We can't do that. So the first pair that we can actually use is A equals to 8 and H equals to 3. And this would check out. So far, there's no contradiction if we use 8 and 3. Let's try the last pair. We could try 4 and 9, but that will result in a contradiction. 9 and 9, because you still add a 1, the T will be 9 as well. So A will be equals to T. We can't work with that. So let's go back to the only pair that works. So if we go with 3 and 8, the T's will have to be 7. We can also fill up the last A. The last A will also be 8. And quite obviously, S plus S giving us 18, the S has to be 9. And our final answer will be shake equals to 93,860. Question 13. The diagram below shows a shape formed from 4 semicircles whose radii are distinct integers. If the shape has a perimeter of 18 pi and encloses an area of k pi, where k is a prime number, what is the value of k? Pause the video here and give this question a good try. So first I'm going to label the radius of the 3 small semicircles as R1, R2, and R3 respectively, and RB will be the radius of the big semicircle, which will be the sum of the 3 small radii. Well, we know that the perimeter is 18 pi, and that consists of the 4 circumferences of the semicircles. So we can add the 4 circumferences, RB pi plus R1 pi plus R2 pi plus R3 pi equals to 18 pi. And if you look at the R1 pi plus R2 pi plus R3 pi, you factorize out the pi, that's going to give us another RB pi. Then 2RB pi equals to 18 pi, RB has to be 9. Then the thing that we're looking for is the area. It encloses an area of k pi. We can express k pi as the area of the big semicircle, half pi 9 square, minus the 3 small semicircles, so half pi R1 square, minus half pi R2 square, and minus half pi R3 square. Since we know that the radii are distinct integers, we can just guess and check from here. So let's guess the tree radius to be 1, 2, and 6, and let's see what value of k we get. Well, we get k equals to 20. That's not a prime number. Let's try again. What about 2, 3, and 4? Well, 2, 3, and 4, that gives us k equals to 26. Not a prime number either. So 1, 3, and 5, that checks out. K is 23, and that's our final answer. Question 14. If the sum of two diagonals of a kite is 100, what is the largest possible area of the kite? Pause the video here and give this question a good try. So first, let's draw a kite with diagonals A and B, and we know that A plus B equals to 100. The area of the kite is equals to half of the product of the two diagonals, so half times A times B. We can replace B with 100 minus A. Now to find the maximum area, we could draw a graph. You'll see that the maximum area corresponds to A equals to 50, right in the middle of this quadratic curve. So replacing A with 50, that gives us 1250. This also turns out to be the area of a square with diagonals 50. Question 15. What is the smallest 5-digit integer of the form the concatenation of 5x20y that is divisible by 33? Pause the video here and give this question a good try. Well, since 33 divides this 5x20y, that must mean that 3 divides it and 11 also divides it. So let's look at the case of 3 being a divisor. That must mean that 3 divides the digital sum. So 3 divides 5 plus x plus 2 plus y. We can simplify that. Next, let's look at the case of 11 dividing 5x20y. Well, 11 must divide the alternating sum. So 11 divides 5 plus 2 plus y minus x minus 0. So we can toss away the 0. We can also simplify this. This would lead us to two conclusions. Either y minus x equals to negative 7. That way the alternating sum gives us 0 and 11 clearly divides 0. Or y minus x equals to 4. That way the alternating sum will be 11 and 11 will divide 11. Well, the first case of y minus x equals to negative 7 is going to be a very bad idea because the possible values like x equals to 8, y equals to 1, and x equals to 9, and y equals to 2, these are quite bad because we want the smallest 5-digit integer, and in these two cases, x is 8 and 9, that's pretty big. So let's look at the other case of y minus x equals to 4. Well, these numbers, we can generate a list of it. X can be 1, y can be 5, x can be 2, y can be 6, and so on to x equals to 5, y equals to 9. So all we have to do is we just sub them back into the case. Well, 1 and 5, does it work? 1 plus 5 plus 1, that's 7. That is not divisible by 3. So 1, 5 doesn't check out. Let's go to the next number, 2, 6. 2 plus 6 plus 1 is 9. So that works. 9 is divisible by 3. So when we sub in x equals to 2 and y equals to 6, that gives us the number 52206, and that's our final answer. Question 16. What is the value of 2020 cubed minus 9 times of 2020 times 2017 minus 2017 cubed? Pause the video here and give this question a good try. So for this question, we're going to need the algebraic identity for the difference of cube. A cubed minus b cubed is going to give us a factor of a minus b multiplied by the factor a squared plus ab plus b squared. So we're going to treat 2020 as a and 2017 as b. So the 2020 cube minus the 2017 cube, that's going to give us the a minus b of 2020 minus 2017, which is 3. And we're going to get this 2020 plus 2020 times 2017 plus 2017 squared. So this serves as our a squared plus ab plus b squared. Now, when we look at the answer, it's going to give us 3 times of the a squared plus ab plus b squared, but don't forget in the original question you still have that minus 9 times 2020 times 2017. That's like a minus 9ab. So we can factorize the 3 from the 9 and bring it in under one big bracket. So we're going to get 3 times of the a squared plus ab plus b squared minus 3 times of a ab. So you can see that there's a like term, the 2020 times 2017, that product is repeated twice. So we can collect them together. So now we have negative 2 times of that 2020 times 2017. And you can see that what we have here is 3 times of a squared minus 2ab plus b squared situation. So we can further factorize this. This will give us a minus b squared, which will be 3 times 2020 minus 2017, which is just 3, and we square it, so it's 3 times 3 squared, which is equals to 27. In the following diagram, ABCD is a rectangle where E and F are points on BC and CD respectively. The area of triangle AEF, denoted by this square bracket AEF, is 2037. If the area of AECF is equals 2 times of the area of ABE, which is equals to 3 times the area of ADF, what is the area of the rectangle ABCD? Pause the video here and give this question a good try. Now for this question, we can just assume that the AECF, the area, is 6 units. Then given the fact that it's equals to 2 ABE, ABE would be 3 units and ADF would be 2 units respectively. We can redraw this. Looking at the entire rectangle, it will be worth 11 units. And since ADF is worth 2 units, if I were to draw another congruent triangle to that blue triangle, just like this would change the entire rectangle to 2 smaller rectangles, where the upper rectangle is worth 4 units and the lower rectangle is worth 7 units. This tells us that the ratio of the length DF to FC would be 4:7. We can repeat this trick again with triangle ABE. It's worth 3 units. I draw a congruent triangle to it in blue, which is also worth 3 units. That divides the rectangle into 2 smaller rectangles of 6 units and 5 units respectively. This tells me that the length BE to EC is 6:5. Now that we know how the length and breadth is divided, we can just assume the entire area of the rectangle is worth 121 units. That is 4 plus 7 times 6 plus 5. With that, we can work out the units for each of the blue areas. So the first triangle ABE is worth half times 11 times 6, so 33 units. ADF is worth half times 4 times 11, that's 22 units. And ECF is worth half times 5 times 7, which is 17.5 units. The leftover area, triangle AEF, would be the leftover, so it's 48.5 units. And that is worth 2037 according to the question. And using proportions, we can work out that 121 units would be worth 5,092. And that's our final answer. In the following diagram, ABCD is a square of side length 64. E is the midpoint of AB, F is the midpoint of EC, and G is the midpoint of FD. What is the area enclosed by the quadrilateral AEFG? Pause the video here and give this question a good try. So for question 18, I first draw a line connecting the midpoint of DC, let's call it point H, to point A, and this line AH will be parallel to EC. We can also see that the line AH must pass through point G, the midpoint of DF, by the midpoint theorem. Next, we can see that this blue triangle in the bottom left, we know the base and the height, it has to be 1/4 of the entire square. And this blue triangle is congruent to this triangle AED, marked in orange. That means that the leftover pale yellow triangle DEC has to be half of the entire square. And since F is the midpoint of the base EC, that means this green triangle DFC is also 1/4 of the entire square. That means the 4 triangles you see right now, they are all 1/4 of the entire area, being the square. So what we can do now is we can divide the green triangle into 2 similar triangles. So we have the smaller triangle DGH and the bigger triangle DFC. They are similar due to the AA test. This will also tell us that the smaller triangle DGH is 1/4 of the entire green triangle and 1/16 of the entire square. This must also inform us that the trapezium below GHCF is 3/16 of the entire square. Now we can look at the area that we want, AEFG. Knowing that the orange triangle is 1/4 the area, the blue triangle is 1/4 the area, and the green trapezium is 3/16 of the area, the leftover piece, AEFG, has to be 5/16 of the entire area. So that would be 5/16 times 64 times 64, giving us a final answer of 1280. Question number 19. Let x be the integer which is the numbers 1 to 81 written from left to right. In other words, it's just the concatenation of all the numbers from 1 to 81. What is the remainder of x when it is divided by 2020? Pause the video here and give this question a good try. So to recap, we have x, which is the concatenation of the numbers 1, 2, 3, 4 all the way to 80, 81. And we have a divisor 2020, which can be broken up into 2 subdivisors, 20 and 101. These are chosen because they're co-prime and they're going to be easy to work with. So we're going to break this question into 2 parts. What would be the remainder when x is divided by 20? What would be the remainder when x is divided by 101? So let's look at part 1 first. We can rewrite x as 1, 2, 3, 4, 5, 6, 7, all the way to 79, 80 times 100. So we're ignoring the last 2 digits, 81. We split them out as 80 plus 1. So you can see that what I've highlighted in red, 100 is divisible by 20. 80 is also divisible by 20. So the first 2 terms are divisible by 20. That means the remainder must be 1. So I write it this way, 1 mod 20, meaning that x has a remainder of 1 when divided by 20. So for part 2, we're going to see what is the remainder when we divide x by 101. And we're going to do this by chunking the number from right to left in stacks of 4 digits. So starting with the first 4 digits from the right, which is 80, 81, we can quickly divide this by 101. We're going to get a remainder of 1. Next, we go to the next 4 digits, 78, 79, but this is in the 10,000s place. So we have to give this the actual value is 7879 times 10,000. 7879 can be rewritten as 78 times 101 plus 1. 10,000 can be written as 99 times 101 plus 1. And this is going to be the critical trick, that 10,000 is just nice 99 times 101 plus 1. So we have expansion here. We have 2 terms times 2 terms. If you expand this fully, you're going to see that every term is going to get a factor of 101 except for 1 times 1. So we know that this 4 digit 7879 is going to give us a remainder of 1 when divided by 101. So let me run this argument again for the next 4 digits, 76, 77. This is in the actual value, we have to times 10,000 square because it is you can see that the 7 is followed by 8 zeros on the right. So 76, 77, I can rewrite this as 76 times 101, the divisor that we're looking for, plus 1. And the 10,000 square, we can rewrite this as 99 times 101 plus 1 square. So we have this expansion, and if we fully expand it, you're going to see that every term is going to get 101 in it, except for one term, and that will be the 1 times 1 times 1. So we know that if we fully expand this, the remainder will be 1. Every other term has a factor of 101. We're going to use this argument all the way to 1011 times 10,000 to the power of 35. So similar argument all the way, 36 times in total. So we can see that all the way till we reach the concatenation of 10 and 11, we're going to get a remainder of 36. Now we're going to look at the concatenation of the next 4 digits, 6789 or 6789. This one's slightly different because 6789 will be rewritten as 67 times 101 plus 22. This one's not so nice. And 10,000 to the power of 36 will give us 99 times 101 plus 1 to the power of 36. And you're going to see that if I fully expand this, every term when expanded, it's going to be a lot of terms, but no matter how you expand, you're going to get 101 in each term. The only term that's not going to get a factor of 101 is going to be 22 times 1, which will tell us that the remainder is 22. And the same argument goes for the concatenation of 2, 3, 4, 5. It's also going to give us a remainder of 22. So that leaves us 1, the leading digit, times 10,000 to the power of 38. This one will give us a remainder of 1. So in total, the remainder when divided by 101 is going to give us, will be 36 plus 22 plus 22 plus 1. So in total, it's going to be 81. So when divided by 101, x gives us a remainder of 81. And this brings us back to our aim. Our aim is to find the remainder when divided by 2020. Essentially, we're looking for a number that gives us a remainder of 1 when divided by 20 and 81 when divided by 101. And we need to combine these two modulos together. So actually, when I started this, I fully expected we're going to do some evil Chinese remainder theorem problem, but it turns out that we don't need it. We can just list out the numbers that have remainder 1 when divided by 20. So that would be the numbers 1, 21, 41, 61, so on. Similarly, we're going to list out the numbers that have remainder 81 when divided by 101. So that would be numbers like 81, 182, 283, 384. And we're going to see when these two lists produce a commonality. And it turns out it's not very far away, because if we just look at the next number after 61, 81 is common in both. So our final answer is actually just 81. Question 20. Let A equals to 1 over 7 times 3.1415 recurring. So 15 is recurring means that we're going to repeat the number 15151515 forever. This is a rational number with recurring digits 15. Suppose this number A can be written as a fraction m over n. Well, it's rational, so it must be possible. So where m and n are positive integers with no common factors larger than 1, meaning it's coprime. What is the value of m plus n? Pause the video here and give this question a good try. Well, for question 20, we can first write down what is 7a. 7a is just 3.14151515 forever. Next, we're going to multiply this by 100 on both sides. So on the left side, I'll get 700a. On the right-hand side, I'm going to get 314.15151515 forever. Next, I'm going to take equation 2 and I'm going to subtract away equation 1. So on the left-hand side, 700 minus 7 is 693 a's left. And on my right-hand side, I'll get 311.01. And you're going to see that all the 15s will kill each other off. They're all dead. So we can say that A is equals to 31101 divided by 69300. We can also see that there's a common factor of 7, so we'll divide away the common factor from the numerator and denominator. If you can't see it, then you should just check carefully whether they are both the numerator and the denominator are divisible by 2, 3, 5, 7. Go down the prime numbers. Alternatively, you can also prime factorize 23100. The same way I've prime factorized 3300 is 2 square, 3, 5 square, and 11. You can double check that the numerator 1481 doesn't have any 2s, 3s, 5s, or 11 as factors to make sure that the numerator and the denominator are co-prime. A pro tip is that if the numbers are big and they are not prime factorizable, you could consider learning the Euclidean algorithm for these big fractions as well. So our final answer, m plus n, is going to be 1481 plus 3300. So the final answer is 4781. Question 21. Ali and Barry went running on a standard 400-meter track. They started simultaneously at the same location on the track, but they ran in opposite directions. Coincidentally, after 24 minutes, they ended at the same location where they started. Ali completed 12 rounds on the track in those 24 minutes, while Barry completed 10 rounds. How many times did Ali and Barry pass each other during the run? Exclude the times that they met at the start of the run and when they completed the run. Pause the video here and give this question a good try. For question 21, if we look at it from a rate point of view, Ali's rate is 12 rounds in 24 minutes. Barry goes at 10 rounds per 24 minutes. So if we look at the track, one way to look at this question is to assume that Ali is stationary. Ali doesn't move at all, and all the movement occurs with Barry, who has stolen his speed force. So Barry has absorbed all of Ali's speed force, and now Barry is traveling at 22 rounds per 24 minutes because we can add the two rates together. So pretend that Ali is stationary and Barry is running, and in 24 minutes he runs 22 rounds. So how many times does he meet Ali? Well, 22 times in total, but we got to subtract the last one. So in total, the answer will be 21. Question 22. If we have some polynomial, so on the left-hand side, it's 1 minus 3x plus 1 minus 3x squared plus 1 minus 3x cubed, all the way to 1 minus 3x to the power of 100. And on the right-hand side, we have expanded it fully. So the expanded form is a0 plus a1x plus a2x squared all the way to plus a100x to the power of 100. For some integers, a0, a1 all the way to a100. What is the value of the modulus of a1 over 3 plus a2 over 3 squared plus all the way to a100 over 3 to the power of 100? Pause the video here and give this question a good try. So for question 22, what we have here is a polynomial identity. The left-hand side and the right-hand side are equal. We can replace the x with any number that we like. So what number do we like? We like 1 minus 3x to be equals to 0. So we substitute x equals to 1/3 on both sides. Why do we like this? Because if 1 minus 3x equals to 0, then the left-hand side is just going to be 0. We're going to get 0 plus 0 squared plus 0 all the way to 0 to the power of 100. So what happens on the right-hand side? The right-hand side is going to look quite ugly. We're going to get a0 plus a1 over 3 plus a squared over 3 squared plus all the way to a100 over 3 to the power of 100. But it turns out, while it's ugly, it's exactly what we're looking for. What I've boxed up in blue is the thing that we're supposed to find. Except that there's this a0 left over, so we still need to work out what is a0. So the blue square is going to give negative a0, which we do not know what is a0. So we need to still find what is a0. Well, if we look at the right-hand side of the equation, we can find a0 if we replace all the x with, yep, you guessed it, 0. So when we substitute x equals to 0, the left-hand side is going to give us 1 plus 1 squared plus 1 cubed plus all the way to 1 to the power of 100. So it's going to give us 100 while the right hand side is going to give us a naught. So the blue square, the thing that we're looking for, is going to be equals to negative a naught, but we're going to modulus it, so it's going to give us modulus of negative 100. So the final answer is going to be just 100. Question 23. What is the value of square root of 27 minus square root of 704 plus square root of 27 plus square root of 704? Pause the video here to solve this third of thirds. So the first thing we can do for question 23 is to simplify the third of square root 704. And this can be broken into 8 times square root of 11 because 704 is equals to 64 times 11. Next, we need to notice something. 27 turns out to be 16 plus 11. So 16 is equals to 4 square. 11 is equals to the square of square root 11. So if we split the 27 up into 4 square plus square root of 11 square, you can see that what you have inside the third can be rewritten as perfect squares. So 27 minus 8 root 11 can be written as 4 square minus 2 times 4 times root 11 plus root 11 square, and that can be rewritten as 4 minus root 11 squared. Similarly, the second third, 27 plus 8 root 11, can be written as 4 plus root 11 squared. So you have a square root and a square. Be careful here when you are cancelling them off. You need to make sure that 4 is indeed greater than root 11. Otherwise, you're going to have a contradiction there because the square root cannot result in a negative number. So in this case, 4 is indeed greater than root 11, so we can cancel off the square and the square root. So we're going to get 4 minus root 11 plus 4 plus root 11. So the root 11s will cancel off. We'll just get 4 plus 4, which is 8. Question 24. Given that m is greater than n and m and n are both positive integers that satisfy m squared minus n squared whole thing squared equals to 1 plus atn, what is the smallest possible value of m times n? Pause the video here and give this question a good try. Alright, question 24. Since we know that m is greater than n, we can rewrite m as n plus k, where k is some positive integer. Now we can look at the left hand side. We're now going to get n plus k squared minus n squared whole thing squared. And this is nice because n plus k squared, when you expand this, is going to give you n squared plus 2kn plus k squared. The n squared will cancel out the n squared, such that when we finally fully expand this, you'll see that you're going to get a quadratic in n. So 4k squared n squared plus 4k cubed n plus k to the power 4. Yes, the k looks ugly, but the n is a quadratic. Instead, think of the worst case. It could have been a quartic, and that would be worse. So quadratic, let's count our stars. It's a good thing. So let's put in the right-hand side back. The right-hand side is atn plus 1. And we can shift this all over to the left-hand side to form our quadratic in n. And since we know that there is some value of n that satisfies this problem, the discriminant has to be greater than or equal to 0. So if we look at the discriminant for this horrible equation, the discriminant b squared minus 4ac is going to give us 16 times, so the b squared is 16 times k cubed minus 20 squared minus 4 times the a, which is 4k squared, times the c, which is k to the power 4 minus 1. Looks quite bad. But if we fully expand this, not that bad, because the k to the power 6 term cancel out. So what we have left is actually just k squared plus 400 greater than or equal to 40k cubed. Now you'll be thinking, how on earth do I tackle this? This is a cubic inequality. Well, we don't really have to tackle this. We can just construct the graph of the left-hand side versus the right-hand side. So if we look at the graph with the k as my x-axis, you can see that the first equation, the left-hand side, k squared plus 400, is just this quadratic graph in red. Not too bad, quite high up because the y-intercept is 400, but it's just a nice quadratic equation. If we look at the right-hand side, it's going to be a cubic equation, and it's just 40k cubed. So it's going to look something like this. So y equals to 40k cubed. And what do we want? We want the red graph to be bigger than the blue graph. And bear in mind, earlier when we started out, we said that m is equals to n plus k, and k is some positive integer. That means k can't even be 0 or negative numbers. So we're only looking at a very small section of the graph where the red graph is above the blue graph. So what we do? We just do what we do best, and that's guess and check. So let's guess k equals to 1. Does k equals to 1 satisfy it? Yes, it does. 1 squared plus 400 is indeed bigger than 40 times 1. What about k equals to 2? Yes, it satisfies. 2 squared plus 400 is greater than 40 times 8. And what about k equals to 3? It doesn't work because 3 squared plus 400 is now less than 40 times 27. So we've narrowed it down that k is either 1 or 2. So going back to the quadratic equation that we've set out before we did the entire discriminant thing, we can just substitute k equals to 1 and k equals to 2 to verify. So if we substitute k equals to 2, you're going to get 16n squared minus 48n plus 15 equals to 0. We are also told that n has to be an integer. So if we try to factorize this, you can just test for a few possibilities, because you know that n has to be one of the factors of 15. So if you can't factorize out n minus 1, n minus 3, n minus 5, or n minus 15, this is a hopeless case really. So you'll see that there's no nice factorization for k equals to 2. So let's hope k equals to 1 does better. So if we substitute k equals to 1, we're going to get 4n squared minus 76n. Well, that's done. Because there's no constant term, we can just factorize out the 4n. That tells us that either n equals to 0 or n equals to 19. N can't be 0 since they are positive integers, so n must be 19. M will be 1 more, so it's 20, so mn is exactly 380. And that's our final answer. Last question of SMO 2020. We have question 25. What is the value of 1 over 2 plus 1 over 3 plus 1 over 4 all the way to 1 over 37 plus 2 over 3 plus 2 over 4 plus 2 over 5 all the way to 2 over 37 plus 3 over 4, 3 over 5, 3 over 6 all the way to 3 over 37 plus 35 over 36, 35 over 37, and lastly 36 over 37. Pause the video here and give this question a good try. So let's call the sum S, and we're going to rewrite the sum S by the bracketing and grouping all those terms that have the same denominator. So those with denominator 2, that's just one of them, is half. Those that denominator 3 will be 1/3 and 2/3. Those with denominator 4, we group them together, so 1/4 plus 2/4 plus 3/4. And the last term, it will be the numbers with denominator 37, so 1 over 37 plus 2 over 37 all the way to 36 over 37. So let's examine one of these terms. Let's look at the third term, 1/4 plus 2/4 plus 3/4. What's so special about this? This is actually the sum of 1 to 3 divided by 3 plus 1. So the general term is actually 1 over n plus 1 times the sum of 1 to n. And we know the formula for the sum of 1 to n. That's n times n plus 1 divided by 2. And you see that the n plus 1 is going to cancel the denominator of n plus 1, giving us n over 2. So if we replace all the things in bracket with n over 2, the sum S is just going to be half plus 2 over 2 plus 3 over 2 plus all the way to 36 over 2. So that's half the sum of 1 to 36. Again, we know the formula for the sum of this arithmetic progression is just 36 times 37 divided by 2, and we'll just divide it by 2 again, which gives us a final answer of 333. And that's the end of the paper. We've come to the end of the SMO 2020 Junior Walkthrough. Do look out for more Math Olympiad videos on this channel, so do subscribe to the channel if you have not done so. Do give this video a like and leave your comments in the comment section below if you have any questions on any of my solutions. Do have a great day of learning.